Let me record. Okay, so discussion 2. So today we will review some of the questions in the first problem set. So we made some additional questions to help your understanding. And then next week we will discuss the new concept, which is the reference dependence. Okay. So yeah, today. So we will solve 3 questions. First question is about rank-dependent utility. And then the second question is about independence axiom. And the third question is about rank-dependent utility again. And then I prepared 3 sub-questions for question 3. So these 2 questions are easy. And then if I have time, then I will come up with claim 3, which is a bit technical. It will be a bit difficult. Okay. So that was the overview. So let me move on. So assume rank-dependent utility with this felicity function, or also call it as a Bernoulli index. So it's the utility for each outcome. And then we also have this weighting function. This is the probability weighting function. Okay, so suppose that we have this function. Is U concave or convex? Is the first question. So this one means this our U function, Ux, is it concave or is it convex? Okay. So what do you think? Is it concave or convex? If Ux is x squared. Maybe you didn't learn about the definition, concave and convex. Yeah. So I didn't mention it. So let me show you a picture first. So if you understand this picture, then you will know everything about concave versus convexity. So suppose that our x-axis, the horizontal axis, is x.
Okay.
Any questions?
No, sorry,
concave. This one is convex. So you will see soon. Actually, when economists talk about concave and convex functions, it's sometimes like it can be sometimes different. But anyway, so in our context, in economics, this is a concave function. This red thing is a convex function. This dotted red line is convex. Okay, so sometimes we call it a concave to origin, something like that. So if we see, if this is the eye, if we see from here is concave, I mean this green line is concave. Also, at the same perspective, if we see from here, this function, this red function is kind of convex. So yeah, so functions that shapes like this, the red line is convex. Functions that shape like the green line is concave. Does that make sense? Using math, it doesn't make sense. This definition, doesn't make sense. So we need another cool definition. So keep this in mind. And then here. So what is concave? Maybe I should make an additional page here. Okay, so this is to discuss concave versus convex function. Okay, oops. So let me draw the picture again quickly. X, U, X. This is concave. And this is convex. So what is concave? Ux is concave if and only if. So this is when you give the definition, you have something like this, two arrows at the both end. So this means if and only if. So this statement implies the statement that I'm going to write soon. And then this statement at the right-hand side also implies the left-hand side. So it works both direction. So U is concave. When is it concave? If alpha ux 1 plus 1 minus alpha ux2 is smaller than or equal to u alpha x1 plus 1 minus alpha x2. And assume that alpha is a positive number. Okay. So this is a definition for a concave function. Looks a bit like unintuitive. So let me show you the intuition for that. If I draw a line like this, dotted line like this, suppose that this is x1. Suppose that this one is x2. Okay. So what is this red star here? The left-hand side of this inequality. It is an average between two function points. So it's average between here and here. So it will be somewhere around here. Okay, so it's like an average between two function values. And what about this? So let me give a notation, star, okay, the left-hand side. And then let me call the right-hand side as 2 star. What is this? It's a function value evaluated at the mean, okay? So at this point, between x1 and x2, this is alpha x1 plus 1 minus alpha x2. In the middle between x1 and x2, you evaluate at this function at this point, okay? So this is 2 star. So using this graph, we can see that if function is has a concave shape, at any line like this, we call this a secant line, and at any line like this, average between two function values is always smaller than the function value evaluated at the mean or at the average value. Okay, so this is the definition of concave function. Does that make sense? This is intuition number 1. It's a better intuition that is suited for this class. Look at the graph. Okay. Intuition 2. Sure outcome is better than the risky outcome. Okay. So if we use the notation that we learned in the class, then this star, let me call this lottery star, which is coming from this left-hand side of the equation. Okay. Then what is this? This can be written as first outcome with a probability of alpha. Second outcome happens with a probability of 1 minus alpha, right? So this is lottery star. Okay. And then what is the second lottery? 2 star. It is, look at here, we have only one outcome, right? This one has only one outcome for sure. So alpha x, I get money, alpha x1 plus 1 minus alpha x2 with for sure 100%. Okay, so this is preferred because u alpha ux1. This was 21st century. Let me copy and paste with our mighty technology. Paste this guy, which is a number, yes, strictly greater than or equal to this number. Let me make it weak preference like this. Okay, so intuition 2 says that it's the same thing, same identical thing. Sure outcome. This one happens for sure. This one is a risky outcome. Okay, because they have the same mean. So in this lottery, 1 star and 2 star, I'm expected to get a same value. However, I prefer a sure outcome. Okay, so this is intuition number 2. So economists sometimes say that if our utility function, this u function, this u guy here, this one, if this is concave, we sometimes say that the person is risk averse in this sense by this intuition number 2. Okay. Intuition 1 is like how we explain concave function using a graph or mathematics. Does that make sense? Okay. So we just learned the definition of concave function. I know that you guys learned this in 100 C or B. So you learned this before, but I just gave a review. What about convex function? If I say same thing twice, you guys will get bored. So I'll just talk about the conclusion. Convex function is it's kind of the opposite case of concave function. So in here, intuition 1, let me just write the conclusion here, which is u alpha x plus 1 minus alpha x2. Now this guy, now if I take a mean, it is smaller than alpha u x1 plus 1 minus alpha u x2. This is the definition. U definition for u being convex. If and only if, yes. I should have made some spaces for this. Okay, so when I do some handwriting, it becomes very unorganized like this. So I was not prepared for this one. Anyway. So yeah, so for the convex function, definition is this. You can see that the inequality is just flipped. Okay, so you can check it later. So the left-hand side and right-hand side is just swapped. And then intuition tells us that in economic sense, this guy is a sure outcome. This guy is a sure outcome. This guy is a risky outcome. So I prefer a risky outcome than the sure outcome. So this type of guy, we call him as a risk-loving agent. He loves risk. Any questions? But this risk-loving and risk-averseness makes sense under expected utility framework. We will see that kind of intuition doesn't work with rank-dependent utility. So we should be careful. So this question is about that concept. Okay, so yeah, so you'll see soon. So is U concave or convex? Yes, a convex function. If you use differentiation, there's much more easier way to see if the function is concave or convex. So let me add some more sentences here. So I'm sorry. So really the last one. A function u of x is bullet point concave if and only if u double prime x is negative. So this is annotation, second derivative of u. So if I differentiate u twice, and then if this is a negative value, then I can say that u is a concave function. This is also true. At any x, okay, let me be precise, at any x. U is convex, if and only if u double prime x is larger than 0. Okay. Let me make a weak inequality. Weak inequality. So if the second derivative is a positive value, then it is a convex function. So there's another way of looking concavity and convexity. So this function, very nice function. This is a differentiable function, twice differentiable. And we can see that u double prime x, let me start with u prime x, step by step. U prime x, what do you get if you differentiate this function once with respect to x? It's du dx. What do you get? Dx squared differentiated with respect to x. Melina said 2x. Very good, very good. It's 2x. If you differentiate twice, then what do you get? So you're differentiating this blue box, a blue circle. Oh, I'm stuck here. Someone should help me here. What do you get if you differentiate this once more? 2, thank you. Yeah, so Melina said 2, very good. 2 is correct. If you don't know how to differentiate a function, that's fine. If you differentiate this kind of form, x to the alpha, you will get alpha x1 minus alpha. If you differentiate once more, then you have alpha 1 minus alpha x1 minus alpha. Alpha minus 1, sorry. Yeah, so if you differentiate the function like this, x to the alpha, then you take minus 1 at the exponent, and then you take that alpha to the ground. Okay. So this is how we differentiate a function. So we can see that this value, second derivative, is a positive value. So this is a convex function. Also, if I draw this ux, then it will be looking like this. When x is 0, ux is 0 because it's 0 squared. If x is 1, then ux is 1 because it's 1 squared. If x is 0.5, then this ux is 0.5 squared, which is 0.25. So it goes beneath this dotted line. If I connect all the dots, you will get this kind of graph. This kind of graph. When I look from the x-axis, it has a convex shape. Okay? So this function, we call it a convex function. So in both ways, you can solve the question. You can draw the function, or you can take a second derivative. Any question? Okay, and then second question. Now, using RDU, what is the certainty equivalent of certainty equivalent? What is this? This is how much sure outcome do you need to be indifferent from taking this lottery? Okay. So, what is the certainty equivalent of this lottery? Then we should first get the RDU. Let me break down into step by step. So get the RDU, the rank dependent utility of 10.5, 0.5. What is this? So the best outcome is 10. So we have 10, U of 10. And then this is the best outcome. So outcome that is weakly better than 10 is 10, only one outcome. So we need to apply G of 0.5 minus a little bit here. Now, there's no outcome that is weakly, that is strictly better than 10. So we have G of 0 here. Plus Now the second outcome is 0. Okay. And then outcomes that are weakly better than 0 is 10 and 0, all of them. And their probabilities add up to 1 minus G of 0.5. So this is a probability of getting an outcome that is weakly better than 0, which is 10. And the probability of 10 is 0.5. So we have 0.5 here. And then if I compute this value, we have 0.25 times 100 plus 1 minus 0.25 times 0. Okay. And this is 50. Okay. Oh, this is, I'm sorry, 25. 25. Okay. Does that make sense? Step 2. I should have made more space here. I thought this was enough. Step 2. Okay, so step 2, get the certainty equivalent. Equivalent. If there's only one outcome, it's a certainty, sure outcome, just one outcome, okay? Then my RDU or expected utility, they're all the same. It becomes U of that certainty. Let me call it C. C stands for certainty. So we need to find the value C such that it becomes 25. Of course, that 25 is coming from RDU 10.5, 0.5 from the step 1. Okay, so it's coming from step 1. So C squared should be 25. What does that imply? C should be 5. If we don't accept negative value, C should be 5. Okay. Okay. So question B is done. Let's go to question C. Is it consistent with risk aversion or risk seeking? Let me add one more option. Neither risk averse or neither risk seeking. I forgot the name for that. That was risk neutral. So if a person, okay, so let me write the definition again, just as a reminder. The person is 1, 2, 3, risk averse if if certainty equivalent is larger than the expected value of the lottery. Okay. Let me copy and paste this 3 times. Risk neutral. If this is the same, if I flip this here, then risk seeking. Also same as risk loving and risk seeking is the same. Okay, so given a lottery, a person is risk averse if certainty equivalent is larger than the expected value of the lottery. So in here, our lottery was 10.5, 0 happens with probability 50%, 0.5. What is the expected value from this lottery? It's just 10 times 0.5 plus 0 times 0.5. So what do I expect to get? Is 5. So 5 is the expected value of the lottery. This blue guy here. What was the certainty equivalent from step B? It was 5. This guy is risk neutral. Okay. So why did our professor make this a very good question? Look at this. What did I say before was that if this function is convex under expected utility framework, this kind of guy where ux is a convex function under EUT, he was risk seeking. Let me write it here as a conclusion. Blue. So conclusion. So after solving all of these questions A, B, C, the main takeaway from this is that under expected utility framework, expected utility theorem, UX being concave implies that the person is risk seeking or risk loving. However, under RDU, this UX being, oops, I'm a typo here, convex. UX being convex does not imply, so it does not imply the person is risk seeking. Does that make sense? Okay. Yeah. So if there's no question, let me go to the next question. This one is easy. Question 2. Suppose that the decision maker is indifferent between two lotteries L1 and L2. Okay, so what was our notation? L1, this sign, wave sign. Yes, L1 is indifferent to L2. Show that on the independence axiom. So suppose the independence axiom is true. She should be also indifferent between L2 and this guy. Let me call it L3. Implies L2, L3. Okay, so we should figure out how somehow we mix L1 and L2 with some other lottery or themselves to get a third lottery like this. Okay? So we should figure out how. Okay? So what I was saying is that suppose that L1 is indifferent to L2, then there should be L2 that is indifferent with L2. Yeah, so let me give you a hint. Then alpha L1 plus 1 minus alpha L2 is indifferent to alpha L2 plus 1 minus alpha L2, which is L2. You can see that this alpha and O minus alpha add up to 1. So it's just adding the same guy twice with weights that adds up to 1. So this guy is L2. And how do you have this relationship? It's coming from independence axiom. Independence axiom. If I'm indifferent between two lotteries, L1 and L2, suppose a third lottery kicks in, and then I mix L1, L2 respectively with a third lottery, then that shouldn't change my preference ordering. That's the independence axiom. Okay. Then what is alpha? is the question. So how should we mix L1 and L2? So look at that L3 is 100.29. So in the end, we are making this L3. 2/3, 50, 1/9. Okay. So if I mix L1 and L2, you can see that this outcome is in L2. Okay. And then it became, and then the probability for this one became 2/3. So I can guess that it should be 2/3 to L2, 1/3 to L1. Okay. And then we can just check. Does it work? For L1, now this outcome 100 only exists in the first lottery. And then for this compound lottery, the probability of getting 100 is 2/3 times 1/3, which is the probability of getting L1. And then second outcome is 60. Now this one, it should be 2/3 times 1. I get 60 for sure if I get L2. And then for the outcome 50, this one only exists in the first lottery, L1. Okay, so it is 1/3 times the probability of getting first lottery, which is 1/3. You can observe that this one, L3, is the same as this mixture. So we found the ratio. Then we go back to this statement. So 1/3 L1 plus 2/3 L2 is indifferent to L2. So yeah, so by independence axiom, this guy should be indifferent between L2 and L3. Does that make sense? Okay, so last question for today. Assume that a person alpha, thank you. So yeah, a person alpha, so we will call each person as alpha, evaluates lottery based on RDU, where UX is just X, and then G of P here is P to the alpha. Okay? So every person have same utility function, this function, but their probability weighting function are different. Okay? So if I call a person as alpha, then his probability weighting function is P to the alpha. And assume that alpha is greater than 1. Is the following claim true or not? Explain. Claim 1. For two people, alpha and beta, where alpha is greater than beta, if the person alpha is indifferent between L and the sure outcome for some C and P1 greater than 0. Okay, so this lottery has two outcomes, X1, X2, and then some positive probability attached here. So if this is true, then person beta also prefers L. I'm sorry. So if L is preferred, if L is indifferent to L hat for person alpha, then person beta prefers L hat to L for beta. So I don't have much time left, so let me just tell you the answer. It's true. So let me start from here. By the way, this question 3 is what I made. So question 1 and 2 is coming from our professor. Question 3 is coming from me. Maybe it can be less related to your exams. Anyway, good to know. Good to know. Good to know about RDU. copy, paste image. Okay, so yeah, person alpha, for person alpha, he is indifferent, or she is indifferent between L and L hat, which implies that R du of L is R du of L hat. What is this? R du of L is U x1 G of P1 plus G. I was going too fast. So suppose that x1 is greater than x2. This claim works for any cases. So x2 can be larger than x1 if you want, but without loss of generality, let me just assume that x1 is larger than x2. Okay? So it can work in the opposite direction. So if then in this case, x1 is the best outcome here. So for that one, the best outcome, we have G of P1, because only x1 is weakly better than x1. There's nothing that is strictly better than x1. So if G of 0 times. Now for the second one, U of x2. Now everything is weakly better than x2. So we have G of 1 minus G of P1. So only x1 is strictly better than x2. So we have GP1 here. Okay. Then just doing this calculation, we have G P1 times U x1 plus G. I'm sorry. We have 1 minus G P1 times U x2. Okay. And what's G P1? We have here. Let me copy and paste this one. No, yeah. Let me just write it here. So G P is P to the alpha. If the person is alpha, then continued. It is P1 alpha U x1 plus, and then U of x1 is x1. So I have x1 plus 1 minus P1 alpha times x2. Now switch the person to the other guy who's beta. For guy named beta, P1 beta times x1 plus 1 minus P1 beta times x2. Okay, so what can we observe? If, let me use space at the right, the color green. If beta is greater than alpha, I'm sorry, it was the other way around. If alpha is greater than beta, then you can see that this function, the G function, the GP function looks like this. If a guy is alpha, it will be looking like this, the convex function. So this is when alpha, this is for the guy alpha. Now let me draw beta first. Beta. And then for guy alpha, it looks like this. This is the guy named alpha. So if alpha is greater than beta, the function becomes more concave, more convex. More convex under the probability weighting function of guy alpha. So this number, P1 alpha, if I compare the value of P1 alpha and P1 beta, then we can see that this number is much greater. Okay, so this is obvious when we see this graph. For the same level of P, we can see that this curve for the beta is always above alpha. So P1 beta is always greater than P1 alpha. Okay, so this number, if I fix x1, this number is getting greater. So the line below is greater than line above. And then now here, x2, it is a smaller number. And then here, I'm attaching less weight for x2, okay? Because as P1 beta goes up, this 1 minus P1 beta will decrease. Okay? And then we have more weight for x1, okay? So in overall, R du of beta is larger than alpha. Okay. Now let us compare the sure outcome. This L hat. Okay. However, this was RD of the lottery, which was x1 p1 x2 1 minus p1. However, for the sure outcome, RDU of sure outcome C happening with 100%. Now this one is the same for both alpha and beta. Okay, so we have all the components here. So for the guy alpha, he was indifferent between this RDU of L and RDU of L hat. However, for the guy beta, you can see that this number has increased. For beta, RDU for alpha. So if I compared RDU for alpha and RDU for beta, we can see that this number was larger. And then for the guy beta, RDU of L hat is the same with RDU for alpha. So they evaluate certainties as the same. Then we can see that this number, RDU for beta, should be greater than RDU of L hat. It should be other way around. So L should be preferred to L hat. That's a small mistake here. So just evaluating this claim, it is false. False. Beta prefers L to L hat. Okay. So for the guy named beta, he will prefer this risky outcome than this certainty equivalent. Okay, so yeah, I admit that this was a bit technical question, but I think this level of question may appear in the exam. Okay, so yeah. So next week I will come back to the reference dependence, and then yes. So thank you for coming. I'll see you guys next week. So let me end the class here.
Thank you, Doug.
Yeah, thank you. Thank you.